Okay, everyone, we are on Tuesday of our first week of actual new material, even though we did have new material prior to this week. I want to look at the three Canvas problems that I put out on the Taylor polynomials, and they're kind of already worked out. So it's going to be a hybrid of here's a solution key, so you could just look at it, I suppose, pause the page and look. Or I'll quickly explain what it is that I've done, and then I'll add in the final step of putting those sigma notations in. So here we go to those problems. Problem number one asked us for a third degree polynomial, Taylor polynomial. So what I like to do, I'll put down my 0, 1, 2, 3, just to look at the n value. That'll show up in sigmas. But 0 means the 0th derivative, and the 0th derivative is basically just the original function. So you could have a 0 derivative. I rewrote the 1 over x plus 2 as x plus 2 to the minus 1. It made the derivatives. Again, you could just kind of watch them develop over the steps here. No chain rule necessary because it's a 1x. So times 1 times 1 times 1. We're evaluating each of the derivatives not at 0. That was the Maclaurin series. But in a Taylor polynomial, we could be evaluating anywhere. Here it tells us to evaluate at x equals -1. So here we are evaluating each derivative at x equals -1. So we plug in for x. We get -1 plus 2, which is 1, and 1 to any power. So these are just 1s, and all we're left with are the coefficients that develop, the -1, the 2, and the -6. As far as we continue here, we're going to always multiply by the 1 over n factorial. That's part of the form of the Taylor and the Maclaurin series. And you do these a while, and it's always 1, and 1, and 1/2, and 1/6. This is 2 factorial. This is 3 factorial, and so on. And then we multiply by the polynomial term, and I found myself having to write this in a number of times for some of your responses. The polynomial term for the Taylor polynomial is x minus the point at which we are evaluating. So in this case, it's x minus -1. And you might see that written in some of your comments. That becomes x plus 1, and that's why all the polynomial terms are plus 1s raised to the appropriate powers. We take these and put them together to write out the actual polynomial. So it's 1 times 1 times 1. That's 1. Then we get a -1 times 1 times the polynomial term. So that's minus x plus 1. 2 times the half. So that's going to be a plus. And it's x plus 1 squared, and -6 and and 1/6 is again 1, so it's minus x plus 1 cubed. This is the third degree Taylor polynomial. The last thing we're asked to do is to write out the sigma notation. We're going to have our n's go from 0 to 3. We recognize that all the terms look fairly similar. They are all going to be x plus 1 raised to the nth power. When n is 0, it's just 0, and we're seeing that right here, 0, 1, 2, and 3. The factorial term is canceling out the coefficients, so we don't need to see that here at all. But what we do notice is there's an alternating sign here, starting with a positive term. And the way we account for an alternating sign, and this is all the time, is with a -1 power, -1 raised to a power. I just need to know, do I put an n or an n plus 1 in this location? Well, I want the 0th term to be positive, so anything to the 0 is +1. That makes the first term negative, and that works, and so on and so on. That's it. Question 2. Question 2, we're only looking for the Taylor polynomial, no sigma notation. Second degree, so I put a 0, 1, and a 2. The function is root x, which I wrote as x to the half, again, to make our derivatives easier as we work our way through. We're evaluating them all because, again, it's Taylor. They have to tell us where. X equals 4. 4 to the half, square root of 4 is 2. This is 1 over 4 to the half, so 1/2 times the 1/2 is 1/4. And finally, when you evaluate the second derivative, -1/32. So we get these values for derivative evaluated at the x equals 4. Here's our 1 over n factorials, 1, 1 1/2. And then again, because it's at x equals 4, we're evaluating the polynomial x minus 4 to the n. So here's x minus 4 to the 0. It's always just a 1. Here it is to the first, and here it is to the second. Put these together, and we get 2 times 1 times 1, so 2, plus the 1/4, x minus 4, and finally, multiplying the coefficients, negative 1/64, x minus 4 squared. And finally, we go to the third problem. Third degree Taylor, 0, 1, 2, 3. E to the negative x is the function. There's a bit of chain rule. Every time you take the derivative, you get e to the minus x and an extra negative 1. So that negative 1 multiplies by another 1, it becomes positive, and you just get a kind of flip-flopping of e to the negative x's. One thing that AP probably wouldn't require you to do, it's probably okay to leave a term looking like e to the negative natural log of 2. However, we should remember, with natural logs, we can take coefficients outside and bring them up front. Here it is showing up as the power now. So e to the natural log of basically 1/2 is just 1/2. So there's a tremendous simplification here with e to the negative natural log of 2. It's a half. We get a negative half, positive half, and negative half. So it just seemed easier to write them this way. Here's our 1 over n factorial, same numbers we've seen. And again, this is being evaluated at a weird natural log of 2 value, but that is x minus the natural log of 2 raised to the powers. If we write these out and just write out the polynomial, we get a 1/2 minus a 1/2 x minus natural log of 2, whoops, there's my 2, a 1/4 x minus natural log of 2 squared, and finally a negative 1/12 x minus natural log of 2 cubed. And this was the most difficult one to write out the summation for. We are going to go 0 to 3, because we're doing 0 to 3 over here. And we are going to be getting our x minus natural log of 2 raised to the nth power, 0, 1, 2, 3. It's this coefficient piece that's a little bit difficult unless we break it back down. If we try to come up with a simple way to do it, 2, and a half, and a half, and a fourth, and a 12th, a little tough. But if we come back to this step, we realize these are all halves, but with an alternating sign. So as we saw, the alternating plus minus, first term positive, so I'll do that as an n. So that takes care of my plus, minus, plus, minus. All of them have a 1/2, and all of them have a n factorial in the denominator. So if I can kind of fit that in here, different color so we can see it, n factorial part of that term. That should do it. Now here's the thing about these Taylor polynomials, just as a quick final step here. They're all done exactly the same way. And the big deal, the big difficulty is really always this part here. And what they'll do to you on the BC exam, if you're going to get a Taylor polynomial, and it's likely that it'll show up somewhere, is they may not just give you a simple, here's the function, find the derivatives. They might give you the function in a strange way. They might give you the function defined in terms of a different function. And so a way to test can you take derivatives is by asking you to start with something a little different here and simply come up with the derivatives first, second, third, as far as they want you to go. And you'll see some of those when you move into the other 2 assignments for the week. You will see a number of problems where this guy is a little bit disguised, or they'll tell you h of x is equal to some other thing, or whatever. So look for those, and all you really want to do is stop, think about, how do I take the derivative with respect to whatever we need to take the derivative of? So it's some review of derivatives, okay? Hopefully that'll help. Later in the week, I'll try to get out and post more solutions. For now, keep working. I'm going to try to keep up with you as you turn things in. I'll try to get feedback to you in whatever method, whatever form you put it out there. All right. Good luck. Keep working.